Good evening, everyone. My name is Anay Ashwin, and I'm a Year 10 student from Hayleybury College in Melbourne. I'm also studying space science through the University of Southern Queensland Head Start program. Today, I'm excited to present the Vena Regolith Sample Acquisition Device, or RSAD, which is a novel proof of concept for Lunar Regolith collection. I developed Vena at the end of 2023 for the ELO2 Big Dipper Regolith Acquisition Challenge, which was delivered by Lunar Outpost for the Australian Trailblazer Lunar Rover program, funded by the Australian Space Agency. This competition drew over 200 participants globally, including PhD students, engineers, and space professionals, and I was fortunate to place third and be one of the youngest competitors. The device had to meet strict criteria. It had to integrate with a 20-kilogram rover, operate on minimal power, collect and store at least 1 kilogram of regolith over 5 days, and deposit the regolith into a tray 5 centimeters off the ground without kicking up too much dust. I also presented this research at the AIAA Student Conference last year, where I won the first prize and also presented it as a poster at the International Conference on Environmental Systems in Prague last month. Before talking about the design, it's important to set the stage for why regolith collection matters in the first place. Establishing a colony on the moon is the world's next frontier. A colony will allow for unprecedented scientific research to be conducted and will also act as a base for humanity to explore Mars and beyond. However, transporting resources from Earth to the moon is prohibitively expensive and a logistic nightmare, with current costs for payload averaging about $1 million per kilogram. In-Situ resource utilization, or ISRU, reduces these costs by utilizing locally available materials. The excavation of regolith is the first step in this process, enabling downstream applications such as oxygen extraction for life support and rocket fuel, manufacturing radiation shielding materials for habitats, and water recovery from ice deposits, especially near the lunar poles. With ISRU in mind, the competition brief specified the operating environment for the rover, the moon's south pole. The moon has permanently shadowed regions, which are craters whose bases never see sunlight. Due to the moon's small axial tilt of 1.5 degrees, the moon has a handful of these craters, such as Shackleton and Shoemaker. Water ice in the moon's permanently shadowed regions has been confirmed by missions like NASA's L-CROSS and India's Chandrayaan-1. The lunar poles hold an estimated 600 billion kilograms of water ice, enough to fill 240,000 Olympic-sized pools. This resource is vital for future exploration, supporting life, cooling systems, and oxygen production through electrolysis. But the moon's south pole terrain is rugged, unmapped in some areas, and cloaked in permanent darkness, meaning any collection systems must be highly reliable, energy efficient, and able to handle extreme conditions. The moon has its own unique set of environmental conditions. With gravity just 1/6 that of Earth, maintaining traction, stability, and fuel efficiency becomes more complex. Extreme temperatures can swing from up to 400 Kelvin during the day down to as low as 20 Kelvin at night, and this demands advanced thermal systems and energy storage to survive the 709-hour lunar night. The moon also has a thin atmosphere, which is only 1/14 as dense as Earth's, and this adds to the difficulty. It affects thermal management, sealing mechanisms, and dust mitigation, which is crucial to avoid machine failures. Finally, the moon's surface is bombarded by ionizing radiation, requiring robust shielding and radiation-hardened equipment to protect the circuitry. Understanding the regolith itself was another major part of my research. Lunar regolith, which is the fine jagged dust covering the moon's surface, presents one of the most significant challenges for the RSAD. This abrasive material is formed over billions of years by micrometeorite impacts, and it can wear down equipment, damaged seals, and clogged moving parts. At the lunar poles, regolith can reach depths of up to 15 meters, with variable properties that complicate excavation, drilling, and mobility. The electrostatic charge on particles smaller than 20 microns exacerbates this issue. Negatively charged by solar radiation, these particles stick to surfaces, creating operational hazards. The Apollo astronauts reported severe difficulties with this moon dust, which adhered to equipment and suits. So, without proper countermeasures, such as sealing, filtration, and anti-static coatings and grounding systems, these particles can cause operational failures. Also, as regolith depth increases, its cohesion and density also rise, causing particles to clump together and, and adding complexity to excavation. Additionally, the presence of agglutinates, which are sharp-edged particles fused by heat and impacts, further intensify wear and tear on machinery. These particles, combined with a regolith's basaltic and anorthositic composition, demand advanced designs capable of withstanding harsh conditions. I had to choose materials that could handle the moon's extremes. That meant thermal resistance to survive the long lunar days and nights, low thermal expansion to prevent distortion, structural stability in vacuum to avoid outgassing effects, and surfaces that would resist abrasive lunar regolith, which was all crucial. From the options here, I narrowed it down to aluminum for the bucket drums, which is light, durable, and thermally stable, and titanium for the connecting arm, which stays strong in cryogenic conditions. Other materials like beryllium or CFRP had advantages, but were less practical due to cost, complexity, or handling issues. Before building something new, I studied existing excavation methods, especially from mining in the Australian outback. In my research, I looked at back and front loaders, scrapers, bucket wheel excavators, augers, impellers, and pneumatic systems. Most of these either relied on heavy traction, which is impossible in low gravity, or required too much power. I then pivoted my idea to the existing teeth and tested design from JPL Swampworks, which is RASA, the Regolith Advanced Surface Systems Operation Robot. I was particularly drawn to RASA and its energy efficient bucket drum design, which offered a proven method for regolith collection and its ability to generate horizontal digging forces, which made it a strong starting point. And thus, the final design was named after the indigenous word for the moon from the people of Bruny Island in Tasmania. Vina is a compact 4 kilogram counter-rotating bucket drum regolith collections and storage system, which is about 30 centimeters wide and 15 centimeters in diameter, which is designed to integrate seamlessly with the lunar rover without affecting mobility or payload. Its aluminum alloy bucket drums endures temperature swings, while indium tin oxide coatings reduce dust-related electrostatic charge buildups. Mylar insulation also manages thermal extremes, minimizing the effects of thermal expansion, and a titanium robotic arm offers cryogenic stability and low thermal conductivity, while warm motor boxes prevent outgassing effects. Venus' innovations came from thinking about how to improve efficiency and durability. It uses a trapdoor mechanism to prevent regular backflow and control discharge, an aluminum mesh filter to block large debris and reduce wear, and scraping teeth optimized for low gravity digging without heavy downward force. These features help achieve collection efficiencies of 80 to 90% while keeping dust hazards under control. So the RSAT operates at an optimal speed of 15 RPM, balancing regular collection efficiency with minimal energy consumption of 1 to 3 watts. This low power demand is critical for lunar missions, where energy resources are extremely limited. The controlled speed ensures consistent excavation performance while reducing mechanical stress on components, enhancing durability in the harsh lunar environment. This design enables extended operation without compromising the rover's power allocation, making a reliable and energy-efficient solution for Regolith excavation. I use Autodesk Tinkercad to model components, and Vina also underwent some iterations and design updates for optimization. I had to keep in mind that Vina would be attached to the Lunar rover, and so, to improve balance, I shifted from having one large drum to two smaller ones. The drum's placement was moved from under the rover to at the front, enhancing robotic arm functionality and ground clearance for better maneuverability and balance. Furthermore, to reduce complexity and risks, a proposed protective cover was removed, eliminating unnecessary weight and the potential for jamming. Internally, a mesh cage was replaced with a trapdoor mechanism and integrated mesh filter, which significantly improved the drum's fill ratio and collection efficiency. Thus, citizen scientists used my CAD files to perform the initial tests with a 3D printed prototype of the Vina RSAD, which showed some promising results in the simulated lunar conditions. It showed an 85% collection efficiency per cycle with minimal regolith backflow. The scraping teeth in particular on the drum's edges worked particularly well. However, the internal mesh slightly reduced collection efficiency. What discharge performance was also solid, though it did require some shaking to release all the regolith particles. Vina is currently at a technological readiness level, or TRL, of about 2 to 3. To move it forward, I plan to 1. Refine the bucket drum system using DEM simulations, 2. Improve the discharge system to avoid the need for shaking, 3. Explore new lightweight materials to increase the storage and capacity, and 4. Eventually test it in lunar regolith simulants at a full scale. The goal is to build a system that's reliable, scalable, and ready for flight. And hopefully one day, my design can play a part in building a lunar outpost using Australia's first lunar rover, River. Thank you.
Thanks very much, Anay. Excellent. We probably have time for a couple of questions. I know you have to leave at 8 o'clock. So I'll try and, anybody want to ask a quick question, please? You don't have to if you don't want to. Alan?
Right. Yeah. Look, that was an absolutely fantastic presentation. Thank you very much. I was very impressed. Hey, what's the uniformity of regolith in terms of particle size and density? How homogeneous is this material? Do we know?
Thank you for the question. So the main thing about regolith, as I did mention, was that regolith will clump together because of its negative electrostatic charge, which means that it won't be very homogeneous. So that is one of the challenges that Vina would have to deal with, because regolith is probably going to be in certain clumps and pockets rather than as a fine dust.
Got you.
Perfect.
Thank you.
Does that answer your question?
It does, and thank you very much. Yep.
Okay.
Going to be an interesting learning curve, I think, with this design for any of those things for that reason, Alan, because they don't understand enough about the lunar regolith.
I remember, Wayne, in the early days of even going back so far as Ranger, there was a suggestion that the regolith might be so lacking in density that it would be like quicksand.
Yep, the lunar module was going to sink. That's correct.
But none of that happened.
Anne or Eva, you've put your hand up. This will be the last one.
Yes, very interesting presentation. I was going to ask about electrostatic issues with the dust, because I'd be expecting the dust to quite possibly be charged. And if you're using metal, for instance, without attempts to take into account those issues, there might be real problems actually retaining or dust rather than significantly sized particles. So I was just wondering what you've been thinking about those aspects.
Of course, thank you for your question. So Of course, lunar regolith does develop negative electrostatic charges due to solar radiation. And so the way that I went about to minimize this was through indium tin oxide coatings. To be honest, I'm not a real expert in this field, but I know I've read that indium tin does do a good job of neutralizing these electrostatic charge buildups.
Certainly spreading them around
Yes.
on conducting surfaces, yes.
Does that answer your question?
Yes, good attempt at least. Yes, perfectly good answer for now at least, yes.